I hope it won't be too formal. I think the first step is to have a presentation by the candidate, and then the committee will ask the candidate questions. Perhaps I can begin by saying that to reassure the candidate, all of our members of the committee thought it was rather a good dissertation. So he's not to be alarmed if we ask a lot of questions.
Okay.
Thank you. You can,
So thank you very much for the introduction, and I would like to thank all the members of the committee for being here for my oral presentation, and also to all the people that has come here today. My PhD is entitled, oh, I can wait. Okay, my PhD is entitled Numerical and Experimental Investigation on Pseudo-2D gas fluidized beds. My supervisor is Antonio Acosta Iborra. And this PhD has been carried out in the University Carlos III in the Department of Thermal and Fluid Engineering under the research group of Energy System Engineering. So I divided the presentation in 7 points. I would like to start with a brief introduction about the fluidization phenomena and the motivation of this thesis, then 5 main chapters of results, and finally the conclusions obtained in this dissertation. So starting with the introduction, fluidization is the operation in which solid particles are transformed into a fluid-like state through suspension in gas or liquid. And a good example of that is the video of the floating duct, of a bad duct that is a bad duct that is immersed in a bed of particles, and the duct suddenly starts to float when the particles are fluidized. Hope it works. Here it is. So that's a good example of the fluidization phenomenon. So there we go. So in particular, one of the most popular fluidization techniques is the gas fluidization of beds. And gas fluidized beds are especially indicated when the gas-solid reaction occurs. But fundamental investigations are needed before reliable models can be developed for the design and scale-up and control of fluidized beds. In particular, a gas fluidized bed consists of a bed of particles containing a column and supported by a distributor. And at very low gas velocities, the particles are stationary and the fluid percolates through the voids of the bed. If we increase this flow rate, we can reach a point where the pressure drop across the bed is equal to the weight of the particles, so the particles are completely supported by the gas flow. This is the so-called minimum fluidization conditions. If we continue increasing the gas flow rate, the bubbles are formed in the bed, and if we continue increasing this gas flow rate, different fluidization regimes appear that can be easily characterized using the pressure drop and its standard deviation. So regarding the characterization of gas fluidized bed, pseudo-2D beds have been of great help in the understanding of two-phase granular systems. The pseudo-2D bed must have a transparent wall in order to allow optical access to the interior of the bed, and possess a small thickness in order to ensure that the visualization is representative of the whole system. Also, 2D simulations require less computational cost than fully 3D system. However, pseudo-2D beds may be not properly simulated in a pure 2D domain. Therefore, a correct characterization of gas fluidized bed is essential for the improvement of the current application and also for the development of new applications. This characterization can be done either experimentally, numerically, or analytically. And I would like to briefly describe the experimental techniques employed in this PhD. So first we have the digital image analysis, where it is allowed a clear identification of the two phases in the fluidized bed, and the bubbles can be characterized based on their equivalent diameter, the bubble centroid position, and the bubble centroid velocity. We also have the particle image velocity, or PIV. PIV can be applied in this pseudo-2D bed because of the transparent wall that allows the optical access to the interior of the bed, and the velocity can be calculated by dividing the displacement of the local particle pattern by the lapse of time between two images. And finally, we have the pressure signal analysis, time and frequency signal analysis of the gas pressure measured in the plenum or measuring the bed or in its plenum is extensively used in research and industry to obtain a large amount of information concerning the bed dynamics. So turning now to the numerical characterization, four main approaches can be found in the literature for the simulation of fluidized beds. First we have the most detailed approach is the direct numerical simulation of the fluid flow surrounding each solid particles and the interaction between them. If we reduce the computational cost and the level of detail of the simulation results, we have the discrete element modeling, which is based on a Lagrangian simulation of each particle trajectory, coupled with the Eulerian simulation of the bulk gas flow. If we continue reducing the computational cost and also the level of detail of the simulation results, we have the Eulerian or two-fluid modeling, where the gas phase and the solid phases are treated as a two interpenetrating and continuum media using the conservation equations of fluids. And finally, we have the discrete bubble models and phenomenological methods, where only the more relevant macroscopic characteristics of the bed are reproduced. For this PhD, in order to choose a compromise solution, we have selected the two-fluid modeling, considering both the computational cost of the approach and the level of resolution of the simulation results. So the importance of pseudo-2D beds for the understanding of two-phase granular system has been stated, but also the validation of the numerical codes to be used for the design and scale-up of the fluidized bed systems requires comparison with real experimental data. So we can define the key objectives of this thesis. First, the study of the capabilities of the two-fluid model to reproduce the behavior of experimental pseudo-2D beds. Second, the use of the two-fluid model simulations to provide useful information that is difficult to measure in experimental facilities. Third, the improvement of the predictive capabilities of the two-fluid models for the particular case of a pseudo-2D bed. And finally, the experimental estimation and quantification of the frictional forces induced by the four walls in pseudo-2D beds. So this block diagram sketches the outline of the thesis. First, we will start with the second part, that is a comparison between simulation and PAB results. And then the PhD takes two different paths. The first one, which comprises parts 3 and 4, is assigned to the study of the bubble behavior. And the second one, which comprises part 5 and 6, is assigned to the study of the particle-wall interaction. So starting with the second part, it is entitled Comparison between two-fluid model simulations and experimental results of a pseudo-2D bed. In this part, two major kinds of information were analyzed, simulation and experimental results, and the simulations were performed in a 2D plane, and the experimental results were obtained in a pseudo-2D bed of 5 mm thickness. So as an introduction, the majority of the works comparing two-fluid model and experimental results are focused on the bed expansion, the pressure signal analysis, and time average solids or gas volume fractions. The mean particle motion is a key factor in the motion and mixing of small and large particles in bubbling beds, but a reduced number of works make a proper comparison between the mean particle motion of experiments and the simulation results. For example, Lee et al. Compared the experimental results from Laberman et al. In a pseudo-2D bed with 2D and 3D simulations. The results indicate that there is a great discrepancy with the experimental particle velocities when the system is just modeled as a pure 2D plane. So in the present part, it is performed a comparison between Eulerian two-fluid model simulation and experimental results of a pseudo-2D bed. The simulation comprises two different well-known closures, the Guidaspo and the Allan-O'Brien track models, and the time average distribution, the size and velocity of bubbles, and the particle phase velocity outside the bubbles are compared. So this slide summarizes the experimental facility employed for this part. The bed is of 0.5 meters width, 2 meters tall, and 5 mm thickness. And the superficial gas velocity selected for the comparison was 1.75 UMF. Considering that the time average bed behavior will be symmetric, only the half of the bed is recorded in order to increase the resolution of the images acquired by the camera. In these images, digital image analysis and particle image velocimetry can be applied, and the time average velocity was calculated as suggested by Laberman et al. With the above expression in order to correct the range of particles inside the bubbles. Regarding the computational model, the software ANSYS Fluent was employed in this part, and the kinetic theory for granular flow was used for the closure of the solid stress terms. As commented previously, two different track models were employed in the simulation results, the Guidaspo track model and the Allan-O'Brien track model. In the right-hand side of the slide, you can see a sketch of the mesh employed for this part and also the boundary conditions selected. So in this slide, it summarizes the main equations of the two-fluid model. First we have the mass conservation of the gas and solid phases. Then we have the momentum conservation of the gas and solid phases, and some of the terms that appear in the momentum conservation, such as the solid stress tensor of the solids of the pressure of the solids of the pressure of the solids pressure, depends on the granular temperature. This granular temperature accounts for the kinetic energy of the oscillation of the velocity oscillation of each individual particle. It is represented with the letter theta and can be calculated with the final expression. So the first part of the results shows the bubble probability maps for the experimental results in the first figure, the simulation results in the figure in the middle, and also it is included the time average solid volume fraction using the simulation for the simulation results. And what we can see here is that the lowest values in these bubble probability maps for both numerical and experimental results appear at the bottom of the bed and near the walls. The highest value of this bubble probability is near the surface of the bed. And paying attention to the third figure, we can see that the bubble probability distribution pattern is quite similar to the mean volume fraction of particles. So to continue this analysis, these two figures shows the bubble probability profiles versus the lateral coordinate in the figure in the left, and the solid velocity versus the lateral coordinate in the figure in the right. In the first figure, it is shown the experimental results represented as points, several simulations, and in the second one it is included both simulation and experimental result, but also is included an experimental result using a higher superficial gas velocity. This is only done for comparison purposes. We can see reasonable good agreement in the bubble probability profile for both numerical and experimental results, but paying attention to the solid velocity, the magnitude of the numerical velocities are one order of magnitude larger than the experimental velocities. Also, the numerical velocities disagree even when compared with experimental results for a much higher superficial gas velocity. So these discrepancies are quite remarkable. So to continue this analysis, the bubble behavior is analyzed. The first figure shows the bubble diameter versus the bed height for the experimental result, the simulation result, and also is included the theoretical model from Shen et al. Proposed for the bubble growth for pseudo-2D beds. And in the second figure, it is shown the bubble velocity versus the bubble diameter, again for the experimental and the simulation results, and the theoretical model for the bubble velocity for different values of phi. So first, different values for the bubble threshold in order to distinguish between bubbles and dense phase in the simulation results has to be selected. So we found that the value of 0.3 for this bubble threshold in the solid volume fraction provides the results most similar to the experimental and the theoretical model. Also, both experiments and simulations predict larger bubble diameter near the bed surface, and the Guidas-Podolak model leads to the closest results to the experimental data in the bubble diameter and velocity. So to conclude this part, two major types of information have been analyzed in this study, the two-fluid model simulation and the experimental results of a pseudo-2D bed. Two different well-known closure models for the gas-particle interaction was used, the Guidas-Podolak and the Siam-Lal-O'Brien track model. We have seen that the two-fluid models is able to predict the bubble growth and velocity as well as the bubble probability distribution. The results also indicate that the time average velocities of the particle phase in the simulated bed are nearly an order of magnitude larger than the velocities obtained from the PAB experiments. And the final agreement in bubble behavior found between the simulation and the experiment does not ensure the same level of agreement in the dense phase velocities in the framework of pseudo-2D beds. So several causes of such discrepancy in the particle velocity can be postulated. So first, the overestimated nature of the particle track models in reproducing the net forces of the gas on a particle in a 2D domain. The high porosity in the regions close to the walls that may affect the behavior due to the reduced thickness of the bed. The effects of the particle wall friction that may be present at the frontal and back walls on a real pseudo-2D bed. And the inaccurate prediction of the particle drop in the wake of the bubbles. So in order to rule out some of these factors, the PhD takes the first path presented in the introduction, which is aimed to study the bubble behavior. This part in particular is entitled Comparison of Bubble Eruption Model with Two-Fluid Model Simulations in a pseudo-2D fluidized bed. In this part, the bubble eruption phenomena is studied. So the simulation results are compared with theoretical models available in the literature as well as with experimental results. So to introduce this part, one aspect worthy of further study is the behavior at the top of the bed, that is bubble eruption and collapse. It has been suggested that the particles are ejected into the freeboard either from the roof of the wake or the wake of the bubbles. And also experimental studies using PAB are used to investigate this bubble eruption phenomena. So the aim objective of this study is to test the ability of the two-fluid model simulations to reproduce realistically the particle velocity around the bubble contour. The analysis is performed for isolated and erupting bubbles and is compared with experimental data and theoretical models for particle ejection. The relationship between the instantaneous gas and particle velocities in the bubble dome is investigated using the results obtained from the two-fluid model simulations. So in this part, the ENFIS code was selected to solve the equations of the two-fluid model. We decided to switch to ENFIS because of two main reasons. The first one is because it is of open source nature. That means that it allows you complete access to the implementation of the equation. And the second reason is because it is specifically designed for the simulation of two-phase granular systems. So in this work, two different bed configurations were studied. The first one is selected as an arbitrary case, and the second one was chosen to match the experimental system reported by Muller et al. So, introducing the theoretical models for particle ejection, Pemberton and Davidson used the potential flow theory to predict the particle flow in the dome formed by an erupting bubble. The velocity potential is governed by the Laplace equation, and the bubble will be assumed to be of cylindrical shape with a radius r, a velocity uv, and an ascending direction theta b relative to the vertical positive direction. Sorry. Also, we have the model of Hung and Handulapur. They assume a linear decrease of the particle velocity with eruption angle. And also, we have the Almendros-Ibáñez model. They modify the model of Hung and Handulapur by including the bubble velocity, the bubble growth, and the direction of the bubble rise. Note that these two models consider that the particles are ejected radially outwards from the bubble. So in the first part of the result focuses on comparing these particle velocities extracted from the two-fluid model simulation for an isolated bubble that is far from the walls and also far from the surface of the bed. So in this figure, it is shown the color maps of the solid volume fraction, the solid velocity, and the vorticity. For a 2D system, the vorticity of the particulate phase is given by that expression, and we can see here how the particles are going from inside to outside the bubble paying attention to the second figure, and looking at the vorticity, we can see that this vorticity is almost null all over the bed, except in a narrow region close to the wake of the bubble. So we can extract the vertical and the horizontal components of this solid velocity, and we can plot it versus the angle of the bubble, and it's plotted together with the prediction of the potential flow theory in these two figures. We can see quite good agreement around the whole bubble perimeter, even in the bubble wake, where the deviation from the bubble shape from a circle is expected to be greatest. So now, turning to the bubble eruption phenomena, the figure shows the time evolution of a simulated erupting bubble, and we can see, for example, that how the particles are ejected from inside to outside the bubble, and that the vorticity here is not only null in the wake of the bubble, but also in the region of the surface of the bed where the bubble is approaching. In this work, it is defined the time is equals 0 in the bubble eruption process as the time where the velocity of the solids in the dome of the bubble starts to decrease. So we can extract these vertical and horizontal components of the solid velocity again, and in this case is plotted together with the prediction of the potential flow theory, the Almendros-Ibáñez model, and the Hung and Handulapur model for two different angle of eruptions. Also, it is included experimental data represented as crosses. First, I would like to mention that the data were obtained for a bubble of equivalent diameter and velocity in the experiments and in the simulation. And, for example, Muller et al. Found that the potential flow theory gave a better prediction for the velocity of particles in the dome of an erupting bubble. Here we can see very good agreement between the experimental results reported by Muller et al., the two-fluid model simulations, and the potential flow theory. So we have checked that the two-fluid model simulation reproduces realistically the solid velocity during the bubble eruption process. So qualitative results from the two-fluid model simulations regarding the gas velocities can be used. The angles that the simulated gas and the solid velocities form relative to the positive vertical direction are studied. So the angle beta is given by that expression, and the last expression can be derived from the potential flow theory. We have demonstrated that it can be reduced to 2 times theta. So this figure shows the gas and particle velocity angles. The filled blue points corresponds to the solid velocity, and the empty red symbols to the gas velocities. Also, it is included the prediction of the potential flow theory and the experimental results. So here, the first thing that we can see here is that the gas and the particles in the dome of the bubble move in different directions. The gas moves radially outward from the center of the bubble, taking the shortest possible path out of the bubble. And the success of the potential flow theory in predicting this angle beta is more than remarkable. So to conclude this part, the motion of particles around bubbles in a 2D bed has been simulated using two-fluid model simulations. For isolated bubbles, the simulated particle motion around these bubbles is found to be described well by the potential flow theory. And for acting bubbles, good agreement is found between the simulated velocity profiles and the PAV data reported by Muller et al. The prediction of this potential flow theory showed the best agreement with the experimental and the simulation results. And we have seen also that the particles are ejected from the dome of the bubble at an angle of 2 times theta relative to the vertical direction. And this observation is consistent with the particle motion in the bubble dome when it is governed by the potential flow theory. So we have studied the solid motion around isolated and reacting bubbles. So to continue the bubble behavior analysis, the gas phase will be studied in this part. This part is entitled Gas Interchange between Bubble and Emulsion Phases in a 2D fluidized bed. The simulation results agree well with the potential flow theory again for isolated bubbles, and a new model is deduced for the gas interchange in multiple interacting 2D bubbles. So especially crucial for the understanding and control of fluidized bed combustors, gasifiers, and other reactors is the characterization of the gas interchange between the emulsion of particles and the bubble phase. Simultaneous measurements of both gas and particle velocities in real beds entail serious difficulties. So, detailed numerical modeling of the bubbling process is a valuable tool that can provide complete information of the gas dynamics. So, the aim of the present part is to study the gas interchange due to advection between the bubble and the emulsion phases in bubbling beds. So, the MFIS code was chosen again to perform the simulations. In this part, 2 different bed configurations are studied. The first one was selected to match the system reported by Patil et al. For the study of isolated bubbles, and the second configuration is a bed arbitrarily selected for the study of isolated bubbles and also for the bubbling regime. So the pressure distribution from the potential flow model for a cylindrical void is compared with the simulation results. So the first figure shows the time evolution of the simulated pressure signal when it is perturbed by a bubble, and the second figure shows the pressure distribution along the radial coordinate together with the prediction of the potential flow theory. We can see that the pressure distribution in the vicinity of an isolated bubble in the simulation fits fairly well the potential flow theory. So introducing now the gas interchange parameters, I'm going to present only results regarding the interchange coefficient, but results also concerning the cross-flow ratio are included in the document, but not here for the sake of brevity. This interchange coefficient refers to the volumetric flow rate of gas going from the bubble to the emulsion phase and is expressed per volume of the bubble. Also, we can obtain an expression for this interchange coefficient derived from the potential flow theory. In this figure, it is plotted the interchange coefficient versus the bubble diameter for several isolated bubbles, and for the 2 different bed configurations, and is compared with the model by Davidson and Harrison. We can see that all the simulated bubbles are in very good agreement with the potential flow model. Therefore, the 2 fluid model simulations can reproduce realistically the gas flow and the pressure distribution through isolated bubbles in accordance to the potential flow theory. So, in order to characterize this interchange coefficient in the bubbling bed, we can say that the presence of multiple interacting bubbles in the bed increases the gas velocities in the vicinity of each bubble. So in this thesis, it is proposed to use a corrective velocity in the Davidson and Harrison interchange coefficient in place of the minimum fluidization velocity. This corrective velocity accounts for the minimum fluidization velocity and for the through-flow velocity. This through-flow velocity can be calculated based on 2 parameters. The first one is the parameter delta, which is a through-flow concentration parameter that accounts for the region where the gas velocity is higher than the interstitial minimum fluidization velocity, and can be calculated with the first figure, which shows a snapshot of the bed with black areas as the region with gas velocity below this interstitial gas velocity. And the second parameter is the parameter psi, which is the fraction of the visible bubble flow over the excess flow, and is plotted in the second figure. The time average value of this coefficient is plotted in the second figure versus the bed height. So for a particular case, we found that the values of the parameter delta MC being equal to 1.3 and 0.394 respectively. So introducing these values in the corrective velocity, we can obtain the expression for the model proposed here, which is 9 times the superficial gas velocity divided by 4 times the bubble diameter. So in this figure, the gas interchange coefficient is plotted versus the bubble diameter for the simulation results for the corrective model proposed here and for the prediction of the potential flow theory. We can see that the potential flow theory the prediction of the potential flow theory is a 50% smaller than the interchange coefficient obtained from the two fluid model simulations, and this can be attributed to the fact that the potential flow theory is developed for isolated bubbles. We can see also that the corrective model proposed here better predicts the simulation result for the gas interchange. So in order to study the superficial gas velocity and the beta aspect ratio, several simulations were carried out with for different superficial gas velocities in the first figure and for different beta aspect ratios in the figure in the right-hand side of the slide. So it is plotted here the normalized interchange coefficient versus the bubble diameter. This normalized interchange coefficient is just this coefficient k obtained from the simulation results divided by the prediction of the model proposed here. We can see that most of the values of the normalized interchange coefficient are nearly constant and close to the unity, but an exception of this case is the one with the highest superficial gas velocity. This can be attributed to a regime transition from freely bubbling to turbulent fluidization. Also, the model proposed here is capable of incorporating the increase of this coefficient k when the superficial gas velocity is augmented. And this interchange coefficient is not strongly affected by the static bed height if we pay attention to the second figure. So in this last section, the results from the 2D simulated bubbles obtained in the two fluid model simulation are extrapolated to 3D bubbles. This is done by revolving each 2D bubble from the simulation over a vertical axis that crosses the bubble centroid. Note that this procedure is only used to estimate the differences between the 2D and the 3D model, and fully 3D simulations with proper 3D bubbles should be needed to complete this analysis. We can derive an expression for the interchange coefficient using the potential flow theory for spherical voids, and the corrective model for interacting 3D bubbles in introducing this corrective velocity is the last expression. So this figure shows these 3 interchange coefficients for the isolated bubbles and for the bubbling regime. We can see that the extrapolation from 2D to 3D shows good harmony within the model proposed and the simulation results. And we can see that the good predictive results of the model shown are remarkable considering the simplicity of this extrapolation. So to conclude this part, we have seen that the two fluid model simulations are able to reproduce the pressure distribution and the gas flow for isolated bubbles. To improve the prediction of the gas interchange coefficient between the bubble and the emulsion phases, the corrected expression was proposed. This corrected expression was proposed for multiple interacting bubbles. A limitation of the model was found when the fluidized bed is working at the highest velocity rates. And the gas interchange in 3D bubbles has been preliminarily estimated using an extrapolation from the 2D bubbles obtained in the two fluid model simulations. The resulting gas interchange coefficient for this extrapolated 3D bubbles is in good harmony with the potential flow theory for spherical bubbles and with the model proposed here for the bubbling regime. But also I would like to remark again that fully 3D simulations with proper 3D bubbles should be needed to complete this analysis. So we have finished now the analysis of the bubble behavior. So now the PhD takes the second path presented in the introduction, which is aimed to study the particle wall interaction. This part is entitled Euler-Euler and Euler-Lagrangian evaluation of pseudo 2D gas fluidized beds. And in this part, a new boundary condition for the particle wall contact in pseudo 2D beds is developed by means of DEN simulations. So in the present part, an additional source of information is introduced, which is the Euler-Lagrangian approach. I would like to mention that all the DN data post-processed in this part has been gently yielded by Professor Christoph Müller and James Third from the Laboratory of Energy Science and Technology at the ETH of Zurich. So it was proved in the previous section that the two fluid model simulation can reproduce realistically the solid motion around isolated bubbles. Two-fluid model and DN simulation were initially compared, showing a high sensitivity to the particle wall contact. This part is included in the document, but I eliminated it here from the presentation for the sake of brevity. So we can say that the particle wall boundary condition is a key factor in the simulations. But it is not clear whether the general boundary conditions for two-fluid models are valid for pseudo-2D beds where both walls simultaneously affect the particle motion. So in this part, the aim of this part is to develop a new partially boundary condition for the solid phase in pseudo-2D beds, and then to implement it in the two-fluid model simulations. So the DEM approach was constructed based on the work of Tsui et al., and the software sphere approach was used to model the collision between particles. And the two-fluid model approach was solved again using the ENFIS code. In this slide, it is summarized the main parameters of the simulation. I would like to remark only that the case 1 will be selected as the base case, and in the other 4 cases, we modify the superficial gas velocity, the coefficient of restitution, and the angle of internal friction in order to check its sensitivity to the new boundary condition. So we can say that the shear force experienced by the bed particles at the wall is related to the gradient of the vertical velocity in the direction perpendicular to the wall. This gradient of the vertical velocity can be expressed as a function of the coefficient of restitution, the angle of internal friction, the vertical velocity at the wall, the thickness of the bed, and the solid volume fraction. So dimensional analysis tells us that the thickness of the bed divided by the solid vertical velocity at the wall times this gradient of the vertical velocity is just a function of the solid concentration, the coefficient of restitution, and the angle of internal friction. So this gradient of the vertical velocity is just a function of the vertical velocity at the wall times a coefficient HW. This coefficient HW can be considered as a partial relief coefficient. So DN data was used to estimate the vertical velocity at the wall and its gradient, and the simulation data were recorded at 50 Hz for a time period of 10 seconds to perform this analysis. Also, the fields near the distributor and near the bed, the surface of the bed were excluded from the analysis, which may not be representative of the solid motion inside the bed. So this figure shows the gradient of this vertical velocity versus the vertical velocity at the wall, and each subfigure plots points within a certain range of solid concentration. Regression of a line in the scatter plot provides an estimation of the value of the coefficient HW. We can see, we pay attention to the first 2 figures, that for lower values of this solid volume fraction, the slope of the regression lines are negative, which means that the magnitude of the vertical velocity increases close to the wall. This trend found for pseudo-2D beds is different than the trend predicted by the Johnson and Jackson boundary condition, which is commonly used in two-fluid model simulation. I would like to note that Johnson and Jackson derived the boundary condition for a semi-infinite volume of particles sliding through a plate, which is not the case of a pseudo-2D bed. So using the slope of these regression lines, the values of the partial relief coefficient can be plotted as a function of the solid concentration. And the best fit was found to be of the form a coefficient A times the logarithm of the solid concentration plus a coefficient B. And those are the results obtained. The first figure shows the cases where the coefficient of restitution and the angle of internal friction were modified, and also it is included the prediction of the Johnson and Jackson boundary condition with a value of phi equals to 0.005 as reported by previous authors as a right value to use in the simulation of pseudo-2D beds. And in the second figure, it is shown the results for the cases when the superficial gas velocity is modified. We can see that the new boundary condition follows a trend different to that of the Johnson and Jackson at low values of the solid volume fraction. We can see also that the coefficient of restitution has a smaller effect than the coefficient of friction on the new boundary condition, and that the effect of the superficial gas velocity is negligible. So this new partial relief boundary condition has been obtained using DN data, and then it has been implemented in the two-fluid model simulation. This figure shows the solid volume fraction, the time average solid volume fraction contour map overlaid with the solid velocity. For the DN data, the two-fluid model using the new boundary condition and the two-fluid model using the Johnson and Jackson boundary condition. We can see that the bed behavior was found to be similar in the DM and the two-fluid model with the new boundary condition, but when using the Johnson and Jackson, the bed shows a different flow behavior when it is compared to the others. to perform a more detailed comparison, in this slide it is shown the bed expansion at the solid velocity. The first figure shows the solid hole up versus the bed height for the three different approaches. We can see how that the DEM and the two-fluid model, when using the new boundary condition, predict similar values of the bed expansion, but it is underestimated when the Johnson and Jackson boundary condition is employed. In the second figure, it is shown the solid vertical velocity versus the lateral coordinate for the three different approaches, and we can see here that despite all the results gives gap values of the same order of magnitude, the bed behavior is different. For example, in the DEM and the two-fluid model with the new boundary condition, we can see two bubble preferential paths, which corresponds to the positive vertical velocities, whereas in the two-fluid model, when using the Johnson and Jackson boundary condition, three bubble preferential paths appear. So the bubble behavior was also analyzed. The first figure shows the bubble diameter versus the bed height, and the second one shows the bubble velocity versus the bubble diameter. And for example, paying attention to the bubble diameter, we can see that there are some discrepancies between the DEM and the two-fluid model when using the new boundary condition, but the results are clearly improved when compared to the two-fluid model when using the Johnson and Jackson boundary condition. In the second one, we can see pretty similar results between the DEM and the two-fluid model with the new boundary condition, but we can see also an unrealistic behavior when the Johnson and Jackson boundary condition is employed. So to conclude this part, a new boundary condition for the solid phase in pseudo-2D beds has been developed. This new boundary condition is based on a partial relief equation fitted to DEM data. Several particle parameters were tested to study their effect on the partial relief boundary condition, and the friction coefficient for the particle wall contact was found to be the most important parameter. At low values of the solid volume fraction, this partial relief coefficient was found to be negative, and thus contrary to the Johnson and Jackson boundary condition. And this new boundary condition was implemented in the two-fluid model and was shown to give more favorable results for pseudo-2D beds than the classical one from Johnson and Jackson. So to continue this, the study of the particle wall interaction, this part is entitled Experimental Quantification of the Particle Wall Frictional Forces in Pseudo-2D Beds. There is a lack in the literature of the quantification of these frictional forces due to the walls in pseudo-2D beds, so we propose here a simple force balance that accounts for the information obtained using pressure signals and digital image analysis to quantify these frictional forces. So to introduce this part, it has been stated in the introduction that the pseudo-2D bed must possess a small thickness and typically have a transparent wall. In this type of system, digital image analysis or particle image velocimetry can be applied to characterize the bubble phase and the solid motion. Also, pressure signal analysis is widely used in the literature to characterize the dynamics of the fluidized bed. But the effects of the front and rear walls on the particle motion can be significant and should not be neglected. So in this part, the pressure signal analysis is coupled with the digital image acquisition of a pseudo-2D bed in order to give an estimation of the frictional forces of the front and rear walls of the bed. So in this slide, it is sketched the experimental setup. It is a 2D bed of 0.3 meters width, 1 meter tall and 130 meter thickness. Ballotini glass particles were used as a bed material, and a digital camera took images simultaneously to the pressure transducers. So this is the force balance that we propose in this section. This force balance tells us that the force exerted by the pressure drop in the bed is equal to, first, the inertia force due to the acceleration of the center of mass of the bed, plus the force due to the weight of the bed, and these frictional forces of the walls on the gas and solid phases. So this frictional force is equal to the shear stress tau times the surface area of the walls in contact with the bed, which is AL. So these frictional forces can be reduced to a coefficient C times AL times omega. This coefficient C can be considered a particle wall interaction coefficient, and omega is the functional form that will tell us the dependence of these frictional forces. Several values of this functional form omega were tested, which was the velocity of the center of mass, the acceleration of the center of mass of the bed, the square velocity of the center of mass, or just a constant. We found that the best choice of this functional form was the velocity of the center of mass, a finding that is in agreement, that is in accordance with the fluid-like nature of the solid motion in a fluidized bed. So if we divide the force balance by the transversal area, we have a pressure balance instead, and the coefficient C can be obtained by comparing the pressure directly measured with a probe, which corresponds to the left-hand side of the equation, with the pressure calculated using the digital image analysis information, which corresponds to the right-hand side of the equation. So, digital image analysis allows us to calculate the position of the center of mass, numerically differentiated to obtain its velocity and acceleration. Besides, a moving average filter was applied to reduce the noise amplified during of the differentiation. The estimation of this particle wall interaction coefficient can be done in two different ways. The first one is the derivation method, which is just the same equation I presented previously, and the alternative way is the integration method that is equivalent to the previous one, but is proposed in order to check the effect of this noise amplified during the differentiation. In this method, instead of differentiating twice the position of the center of mass, we integrate twice the pressure signal measure. And this is the results obtained. The figure shows the time evolution of the pressure signals. The blue line corresponds to the pressure directly measured with a probe inside the bed. The red line corresponds to the pressure signal, to the pressure calculated using the digital image analysis information, but without considering the frictional forces. And the black line corresponds to this pressure calculated using the digital image analysis, but including these frictional forces. We can clearly see that if we do not consider the effect of these frictional forces, the red line cannot reproduce the behavior of the blue line, which is the pressure directly measured with a probe, but if we include them, which corresponds to the black line, the results are clearly improved. So also, in order to check the consistency of the force balance proposed in the theory section, several simulations were carried out. The first simulation is a 2D simulation, that means that the front and rear walls are not considered. And the second one is a 3D simulation where the four walls are considered, but applying a free slip boundary condition for the solid phase. In these two figures, we can see that the effect of these frictional forces is not present. But if we change the free slip boundary condition in the 3D simulation for a partial slip boundary condition, we can clearly see that the effect of these frictional forces is present now. Also, the behavior of this pressure signal is quite similar to that obtained in the experimental results, and we can see, as we have seen in the previous figure. So, a set of experiments were done for a range of superficial gas velocities, bed aspect ratios, and particle sizes. And the figures here shows the results obtained using the derivation method, but similar results are obtained using the integration method. We can see that the coefficient C is relatively sensitive to the bed aspect ratio and the superficial gas velocity, despite some atypical points that appear at low and high superficial gas velocities for the smaller and medium-sized particles. Also, paying attention to the scale of each figure, we can see that for the smaller particle sizes, we have an average value of C around 55 kilograms per square meters per second. In the medium-sized particles, around 65, and for the bigger particles, around 110. So we can say that the coefficient C increases with the particle diameter. So this mean coefficient C can be modeled as a function of the particle diameter as a first approximation, and is used to fit a function that models this coefficient C versus the particle diameter. In this figure, now it is included the results using the derivation and the integration method, and we can see that both methods give similar results. And in this figure, the vertical bars denote the standard deviation of the experimental data from the mean. Also, we can quantify these frictional forces relative to the other forces in the bed, and this is done calculating the normalized standard deviation of each of the pressure terms shown in the force balance. This normalized standard deviation is just the standard deviation divided by the weight of the particles. And we can see here that the frictional force is not negligible in the force balance, increasing its relative contribution when the gas velocity is augmented. We can see also that the contribution of these frictional forces can be even larger than the contribution of the acceleration of the bulk of the bed. So to conclude this part, the frictional forces exerted by the front and rear walls on the solid of the solids of a pseudo-2D bed has been characterized. These frictional forces resulted to be proportional to the velocity of the center of mass times a particle wall interaction coefficient. This coefficient was found to be low affected by the superficial gas velocity and the bed aspect ratio, but strongly depends on the particle diameter. These empirical results evidence that the friction of particles with the walls plays an important role in the pressure fluctuation measured in a pseudo-2D bed. So now I would like to start with the general conclusion obtained in the dissertation, and to summarize all the things presented here in in the presentation. So in this dissertation, numerical and experimental investigation on pseudo-2D beds were performed to gain knowledge about the behavior of pseudo-2D bed systems. In the first part, a comparison between two fluid model simulation and experimental results in a pseudo-2D bed were performed. We found good agreement with regard to the bubble growth and velocity, as well as the bubble probability distribution. But we found that the time average velocities of the particle phase in the simulated 2D bed are an order of magnitude larger than the velocities obtained from the PIV experiments. So these discrepancies found between the experiments and the simulation regarding the mean velocity of the solids may be caused by several factors. In order to rule out some of these factors, the motion of particles around bubbles from two fluid model simulations were analyzed. For isolated bubbles, we found that the simulated particle motion around the bubbles is found to be described well by the potential flow theory. And for acting bubbles, good agreement is found between the simulated velocities, the experimental PIV data, and the two fluid model and the potential flow theory. To continue with the bubble behavior analysis, the gas phase was also analyzed. We have seen that the 2D simulation can reproduce realistically the pressure distribution and the gas flow for isolated bubbles, and a new model was proposed for 2D interacting bubbles when the bed is working on the bubbling regime. Also, we have seen that the effect of the front and rear walls on the bed may be the cause of the discrepancy between the 2D simulation and the pseudo-2D measurements. So, we have proved that the usage of the classical boundary condition was unsuccessful to reproduce the behavior of pseudo-2D beds. Also, DN simulation data was used to extract this particle wall interaction, and a new partial relief boundary condition was developed. This new partial relief boundary condition was found to be contrary to the behavior yielded by Johnson and Jackson at low values of the solid volume fraction. This new boundary condition was also implemented in the two fluid model simulations and was shown to give more favorable results for pseudo-2D beds. In the last part, an experimental quantification of the frictional forces due to the walls on the solid phase of a pseudo-2D bed was performed. The pressure drop measured in the bed was linked with the acceleration and velocity of its center of mass obtained using digital image analysis. These frictional forces were found to be proportional to the velocity of the center of mass of the bed times a particle wall interaction coefficient. This coefficient C was found to be very sensitive to the particle diameter, and the contribution of these frictional forces was found to be even larger than the fluctuation induced by the acceleration of the bulk of the bed. So, as a final remarks, overall, the results of this dissertation indicate that the numerical and experimental observation of pseudo-2D beds should be interpreted with caution. The physics occurring in a pseudo-2D bed is substantially affected by the presence of the front and rear walls of the bed. And this thesis has revealed that the effects exerted by the bed walls on the particles are not negligible and can affect the motion of the dense phase, as well as the pressure fluctuations in the bed. So, therefore, it is essential to resort to specific particle wall interaction models capable of describing the combined effect of all the bed walls in this type of beds of a small thickness. So, as a future work, first, the points regarding numerical investigations. First, to generalize the new developed boundary condition, a natural extension of this work is to study the effect of the thickness of the bed and the particle diameter. Also, recent direct or indirect experimental results for the gas interchange for the bubbling regime could be compared with the model proposed in this thesis. And it would be interesting to check if the effect of the front and rear walls on the motion of objects immersed in the fluidized bed is important or not. So, the future work regarding the experimental investigation, future studies varying the thickness of the bed should be performed to verify experimentally the effect of the thickness of the pseudo-2D bed on the wall friction. And these frictional forces experimentally estimated in the pseudo-2D bed may be related to a variation in the minimum fluidization velocity as reported by Sanchez Delgado et al. So, finally, as a direct output of this dissertation, this is the journal publication we have obtained, and also this conference presentation. So that's all, and thank you very much for your attention.
to begin by thanking the candidate for a very lucid exposition of his rather comprehensive work. I think that the next task is for us to ask questions, and I think the order of questions is Professor Kuipers asks first, Professor Hayhurst second, and I have a few questions of my own. So can I call on Professor Kuipers to...
Thank you, Mr. Chairman. Dear candidate, first of all, I would like to congratulate you with the completion of this thesis. You have done a massive amount of work. Some people only do simulations, others do only experiments. You do both, and you also do different types of simulations, so I think that's a big achievement in itself. But of course, I have not come only to convey compliments to you, I have also a couple of questions. My first question is related to the multi-scale approach, so the various models you can use for modeling fluidized beds. You have this figure on page 10 of your thesis. It was also on your slides. And maybe you could be so kind to explain briefly the strong and the weak points of these various types of models.
Sorry, I was setting
the strong and weak points of these 4 types of models you have indicated in your thesis. So what are the strong and the weak points of these 4 types of models?
That's a very good question. For example, regarding the first one, which is the DNS, obviously the computational cost is the great disadvantage. And also, if my experience with the things I've deal with regarding this DNS simulation, I've checked that there is not that easy to simulate a proper fluidized bed. I think it's quite difficult. There is some problems with the Mach number, which I think is quite weird in the simulated bed. But the good points can be the very detailed solution that you can obtain, but it's obviously quite difficult to obtain.
Okay.
Regarding the DEM, also the computational cost, if you don't have a proper cluster to carry out the simulations, I think this is the great disadvantage, and maybe the drag models employed for this simulation. I'm not completely sure how, well, even also in the two-free model simulation, I'm not completely sure how the drag model reproduce completely good the drag between the particles and the gas. The good point of this discrete element model, for example, compared to the two-free model, is the level of detail of the simulation results. And if we go to the two-free model, well, I have shown all over the thesis all the disadvantages of this kind of modeling. But the good points can be the computational cost. Most of the simulation, I carried out most of the simulation in a desktop computer. And regarding the DBM models, well, it's only the good points is just to have a first view of the system you want to implement or to build or whatever. But you don't have so many details of the simulation results, because you only have results concerning the bubble dynamics. So the good point is that you can have results in maybe one morning, but you don't have so many details.
Okay, thank you very much. I think that's very clear. A follow-up question on this scheme is the connection between the models. You can present them as independent models, but I think in reality there is a lot of crosstalk between these models. And so can you give 2 examples of how these models can communicate to each other? I think in your presentation you already gave one, so that we can exclude here. So the boundary condition, I think that's a very good example. But maybe you can give 2 other examples of how, let's say, the more detailed models can help us to improve the physics represented in the coarse-grained models.
For example, using the DNS, you can extract the exact particle, the gas particle drag to implement it, for example, in the DEM. And this, it has been shown that this drag has been overestimated using the DEM. But for example, you can properly calculate it using the DNS. And for example, you can use the two-fluid model simulations to check the discrete bubble models. It has been shown that the two-fluid model reproduce reasonably good the bubble behavior. So as the DBM model is based on the bubble behavior, you can compare both models to check if the DBM is reproducing well the bubble motion.
Okay, thank you very much. I think this is a very clear example. I have a more detailed question on the continuum model, the two-fluid model. And you used for that the MFIX, or the ANSYS fluent code. And a very important parameter in this model is the restitution coefficient. So the ESS, as indicated in your table on, I think, page 26 of your thesis. And the value you take is 0.9. And typically you use glass type materials, so Ballottini in your experiments. And I wonder, why did you take 0.9? Because it's not a very typical value for the coefficient of restitution for glass-like material. It's more 0.97. And when you look at the normal coefficient of restitution, it's typically having a value of 0.97 if you do independent impact experiments. But nevertheless, you use a lower value of 0.9. Why is that? Can you explain that to me?
Yeah, this can be for many reasons. I would like to summarize all of them.
Okay.
So first, in this first part of the thesis, we try to study just the standard models that you use to simulate the 2D bed, and the standard value for the restitution coefficient was 0.9, so we decided to keep it. But an extra simulation was carried out using a restitution coefficient of 0.99, and we didn't find so many differences. I mean, the best discrepancies found in this part is regarding the solid velocity, and it was not fixed using a different restitution coefficient. This is only attributed to the missing of the front and rear walls. But also, for example, I've checked that in the literature there are many works using different values of the restitution coefficient, from 0.8 to 0.99. And each author gives a different value of them. So I decided just to use the default value, as in my experience, I checked that there is not so much differences between using the different values of this coefficient of restitution.
But do you think then that this is a fitting parameter or a parameter which we should, let's say, determine in a other way?
In an experiment?
Yes. So is it a fitting parameter? The
It can be both.
Can you play around with it? Or is it a constant which is basically dictated by some independent experiment?
That's the tricky thing of the two-fluid model, because you can measure it, but as you are introducing it in many closure models in the two-fluid model, maybe the exact value you are measuring is not the exact value you have to set in the, you have to input in the closure models to fit all the two-fluid model to your data.
But let's focus then on the original, let's say, formulation of the kinetic theory model. What is the meaning of the restitution coefficient in the original model? Do you know that?
I cannot answer right now. I have to check all the equations. I don't know.
That's the normal coefficient of restitution. So
yeah,
that is basically what you should put.
One, yeah.
And of course you neglect then the friction between the particles, which is not accounted for, but normally you should set the coefficient of normal restitution in the kinetic theory, which is 0.97 for glass-like materials. Yeah. I have one final question related to Chapter 2, and that's what would happen if the coefficient of restitution would be set equal to 1? Could you imagine such a situation? So if you would have ideal particles, of course they do not exist on Earth, but in a computer simulation you can play around with the parameters and set it to 1. What would happen? Can you speculate about that?
I think I did the simulation, but it was done like 4 years ago, so I'm not completely sure, but I think the simulation diverges. So I cannot, the simulation crashed.
Oh, okay.
So in the first time steps.
That's a pity. It should not crash. But let's go to the microscopic situation. When you have ideal particles with no dissipation, let's say, would it be reasonable to expect that you have heterogeneity in the system? So small scale voids, which later on then can possibly develop into big bubbles. But when you have this ideal, let's say, collisions, would you expect heterogeneity in the system at all? Heterogeneity means existence of small voids and bubbles.
I really don't know. I don't know.
Okay. Maybe you can speculate a bit.
We can speculate, but I would like to think about that a bit more before answering anything completely crazy. But I don't really know what can happen with an ideal coefficient of restitution.
Okay.
I really don't know. I really don't know.
Okay, well, then I can share the answer with you. What you will get then is no bubbles at all. You have
No bubbles at all.
dissipation, and there will be no void formation at all. Also in the kinetic theory-based model. In the DM model, which has been used also in this study, you can do it very easily, and then you'll see that there is no bubble formation, so no large-scale instability. No bubbles, no large-scale instability.
I will retry my simulation with a coefficient of
Okay,
0.1 to check it.
that's a good thing to think of. Thank you. Okay.
Thank you. I should be using this, shouldn't I? First of all, some general questions about your apparatus and equipment and so on. I noticed that you always use ballatine, where the particles are spherical, and so they have special properties like they can roll and so on. How different are ballatine particles going to be from, say, sand particles? Did you ever do any experiments with sand particles?
That's a very good question, but it's almost impossible to do that because in the framework of a CO2 bed, you can do experiments in a 3D bed with ballatine glass particles and also with sand, but you cannot put sand inside the CO2 bed because the sand, as it is not perfectly rounded, it will damage the transparent wall. Okay. So you won't be able to see properly with the images what is happening inside. The point why I think is quite similar. If you put the ballatine glass particle, for example, in a 3D bed, you will obtain the similar results regarding the bed dynamics, but what you cannot check in the 3D bed is the solid velocity, well, as far as our experimental facility, with regard with the experimental facility we have, because we have no access to the interior of the 3D bed. So we cannot check if the 3D bed with the sand is equal to the ballatine glass particle, but regarding the solid motion, but I think it is regarding the bed dynamics related to the bubbles and so on.
Well, for instance, you end up in a later chapter worrying quite a lot about frictional effects at the walls. Now, you're going to have quite different frictional effects, I imagine. Would you like to tell us what differences you would expect between ballatine and sand particles?
Probably higher friction forces. Because of the not rounded shape of the sand, you will expect greater frictional forces. But the point is, I quantify these effects because in this kind of system of pseudo-2D bed, most of the people use ballatine glass particle because of that, because of if you are using sand, you will damage the transparent wall. But for example, in a 3D bed where you are using sand, this effect can be negligible because the walls are far away from all the system, and the ratio of the area in contact with the volume of the bed is quite reduced compared to pseudo-2D beds. Mm-hmm. But I think these forces will be higher if using sand. But if you try to put it in a 3D system, it will be completely negligible.
Okay. Your distributor, you have perforated holes, but then you mentioned the other day to me that you sometimes have a gauze. And was this gauze above the distributor?
What do you mean with gauze?
Well, you produced, talking to me the other day, a wire mesh.
The metal mesh.
But you say nothing at all in your thesis about
That's
a wire
true.
mesh, and so this is meant to be able
that's true. Maybe
enable me to reproduce your results.
That's very true. I feel sorry about that.
Was the wire mesh sitting on top of this?
Of the distributor, yeah.
Of the distributor with the holes in.
Yep.
Yeah.
It is the distributor with the perforated holes, and then we put the mesh, the metal mesh, and it is glued at the sides of the distributor, and all around the sides of the distributor, and is completely on the top of, is perfectly on the top of the
Yeah,
distributor, so
yeah.
we avoid the blocking of the holes
Yeah.
of the distributor.
Well, I suspect it's-
that's true. I miss it to
I
put it on
suspect
the
that mesh is having a major effect.
Yeah, that's true. I feel so sorry about that. We completely missed that point on the experimental facilities. Yeah, it's
Why didn't you use some porous metal for your distributor?
because our bosses doesn't let us to use.
Sorry?
Our bosses doesn't allow us to use. Well, it's a joke. We typically use perforated plates, and I thought from time to time to use a porous plate, but as all the beds we have made has been constructed with distributor plates, our technician has more experience in building that kind of beds. So we have not used yet this porous distributor. Mm-hmm. But I would like to use that because I think it gives a better performance. You have the homogeneous, the inlet of the velocity is completely homogeneous, so you don't have these problems of holes blocking and so on. But we haven't checked which company can sell us, for example, a porous material to put in to be properly built in the fluidized bed. But I would like to do that.
Well, it makes comparison between experiment and modelling much easier.
Yeah, it is because
and it's actually quite difficult to acquire. I'll send you some.
Thank you.
One of the things that interested me reading your thesis is you quite often talk about particles raining through a bubble. Do you literally mean that, or do you mean that you see particles in the gap between a bubble and one of your walls?
No,
there is a difference.
No, it's just the particles that are raining inside the bubble, not the cloud, inside the bubble.
How do you know they're inside the bubble?
Because you can see you can see it in the images that you can see some certain particles that are inside the bubbles. And for example, if you perform the PAB calculation on all the solid on all the image, and you account for this velocity of these raining particles inside the bubble, it will give you very high velocities, which is not representative of the solid motion in the dense phase. With the motion of the dense phase, the whole motion of the dense phase, because a single particle may create inside the bubble a very high velocity, which is completely unrealistic of the dense phase motion. But some single particles inside the bubbles.
I don't think I've understood how you can conclude that they're actually inside the bubbles.
Sorry?
I don't think I understand how you can conclude that the raining particles, I know you can see particles going vertically downwards, but I'm a little puzzled how you're so sure that they're inside a bubble.
Sorry, but I don't get it very well.
When you look at your experiment,
Yeah?
you see a bubble,
Yeah?
and in front of the bubble are particles moving vertically down.
Yeah.
Now, the question I'm asking
so if
is,
those particles correspond to the
are
bubble
the
or
particles inside the bubble, or are they between the bubble and the walls?
Oh, that's a very good question.
Because you assume that they're actually inside the bubble,
Yeah, that's true.
which is a violation of the two-phase theory.
It is.
So it's an interesting question.
Yeah, I think it's a very difficult question, I think. But I think it is, those particles are inside the bubbles, and...
How do you know?
You really don't know. I think you have to, because if you consider those, you cannot know it, but if you consider those particles inside the bubbles, the mean solid velocity will be completely unrealistic. So you have to remove these outliers, some kind of outliers. So do that just based on experimental findings. So I think in the end you really don't know. It's quite difficult to distinguish if the particles are raining from inside the bubbles or corresponds to the movement of close to the wall.
Thank you very much. I had a question around page 40. Now, whatever was it? You've got a graph. You've got a graph on page 40. I mean, it's obviously going to be difficult to reproduce this, but it was a very interesting graph where you're plotting the diameter of a bubble against its height above the distributor. And things are going up, increasing, and then decreasing.
Yeah, that's a more easy question than the previous one.
Well, what is going on?
This is because at that height, you are getting the surface of the bed, so the bubbles break, and the things you are capturing near the surface of the bed are not proper bubbles, so that's because the curve are going down. So the right values you have to take into account are up to a value of 0.3 in the bed height, because this is the static bed height that I set it in the experiment and in the simulation.
Where does the freeboard begin in that?
Roughly at 0.35.
Oh, okay. So this decline, this fall in bubble size, is in the freeboard.
Yep.
Yeah, I see. Because it's not obvious from looking at the graph that that's the case. So it's a freeboard phenomenon, and you're trying to identify bubble diameters in the freeboard there.
Not really. This is more an artifact of the calculation than real data. But for example, if a bubble erupts or the bubbling of the bed is fluidized and so on, and for example, a certain amount of particles are above the surface of the bed, in the calculation you can consider that as a bubble, which of course is not a bubble. And it can be a very reduced diameter and can reproduce this is the cause of these values of the bubble diameter that goes down when at heights from the distributor.
Okay.
So it's more an artifact than a real, but it's quite difficult to eliminate it from all the images acquired in the experiment.
Yeah. I want to ask you about the ejection of bubbles from the bed, and because you had quite a bit to say in your presentation about that. I mean, one of the questions you raised in your presentation is when you look at the particles ejected into the freeboard, do they come from the dome of a bubble or from the wake?
Most of them comes from the dome of the bubble, because I've only studied isolated bubbles. The particles ejected from the wake are, for example, when a couple of coalescent bubbles are erupting.
Okay, because you didn't quite answer that question in the thesis, in the way you've just answered it there.
Yeah, that's true.
You left an implicit answer, I think, really. If you were to track the rise of a bubble as it disengages from the bed, and if you had by magic a device to measure the pressure in the bubble as it breaks through the surface, what would the pressure, a plot of pressure against time, look like?
Let me think. It depends, but because the pressure, for example, So this is the figure in this slide is the time evolution of the pressure signal that you are measuring a point when a bubble crosses.
But you're sitting here at one height, aren't you?
Yeah. So if you go with the
bubble, and follow its pressure with time.
So I think the pressure will be reducing until you reach the surface of the bed.
And when it breaks,
It is
through the
equal to the
surface?
atmospheric pressure. When the bubble just breaks and you are in the surface, in the freeboard, is just the atmospheric pressure.
Because sometimes people talk about bubbles as they break the surface almost exploding, as if there is a
So-
change in a drop in pressure.
Maybe in experiments, but I think not in the simulation, because in the simulation, in the two-fluid model simulation, due to the fluid nature of the solid phase, the bubble does not erupt that violent, to say in some way. It's more like this tries to erupt, but it splashes. So you can see it better for example, in that figure. So the
Yes.
bubble is erupting, but when the bubble is break, it's not some kind of super ejection of the particles. It's more like they diffuminate.
Okay.
So it's not that violent eruption of the bubbles, but only because of the fluid-like nature because of the two-fluid modeling.
Thank you. I had a question on 103. Now, let me just see what that was. Oh, yes. On page 103, you make a note of an effect as you change the superficial velocity towards 3 UMF. And something happens. I've gone and forgotten what happens. It's the interchange coefficient that's changing.
Yep.
And you attribute this to turbulence. I'm most surprised that turbulence occurs at 3 UMF. Would you like to justify that?
Well, it's not just the turbulent fluidization, it's just some kind of regime transition from the bubbling regime to slugging or turbulent, because slugging or turbulent can be a bit mixed between them, and it's not that easy to distinguish between slugging and turbulent with some particular, with certain particle kinds. So I attributed this just to a change in the fluidization regime, and I wrote that it is just a regime transition from freely bubbling to turbulent fluidization, but it can be considered also slugging or a different bubbling regime than the bubbling regime.
Okay. Well, you know that the interchange is quite different for tiny bubbles and big bubbles. I just wondered if the bubble size was changing as you increase the superficial velocity. Maybe you have big bubbles appearing rather than turbulence appearing. I don't know. It's in principle a possibility.
Yeah, you will have bigger bubbles because the velocity is higher, but I didn't check the exact value of this interchange coefficient. When the velocity is higher, what I check is the prediction of the model I propose with regarding to the prediction of the two-fluid model.
Yeah.
So what I check is that the value I obtain using the two-fluid model is equal to the value of the value predicted by the model I propose, but I didn't check actually what is the real number of this interchange coefficient where the bubbles are bigger because of the velocity is high.
Right. Okay. I'm coming towards the end. I've got a question at the end of chapter 5 on somewhere around page 130. And what you've been doing there is you've been comparing the results of one model with another. And somehow or other, you never really bring a comparison in with experiment. And there's something philosophically wrong with this sort of approach, where you avoid comparisons with experimental facts.
Yeah, that's true, but one of another plan is to extend this analysis and also to compare with experimental results. But the point of that chapter was to extract the particle wall interaction that is only possible with DEM or, for example, DNS simulations. You cannot extract that particle wall interaction, for example, in the experiment, because it is almost impossible. So you can do it only with a simulation that goes to a level of detail of the solution, goes to a deeper level of detail of the solution. So I decided to use the DEM data to extract this particle wall interaction and to implement it in the two-free model, but just to compare both models to check the differences. But obviously, we will have to check it with proper experiments. And my plan in the beginning with that part was to compare it with experiments. I did it in one stay when I did in Zurich in Switzerland. And I did the experiments. I take all the experimental data with me to here. And then when I was here, I checked that the experimental facility was wrong. Okay. So that's the point what I decided to go more into detail of the particle wall interaction. And I keep at one side the comparison with experimental data. But obviously, it will be quite interesting to compare and to validate all these findings with experimental data. Yeah. But what you cannot, for example, the only thing you can validate is, for example, the bed expansion. That is quite easy to compare, the solid velocity. But what you cannot check in the experimental results is this particle wall interaction that I extracted using the DEM data.
I see your problem. A quick question around 139 when you're discussing these frictional forces at the wall. If you take these frictional forces at a wall with your ballatine, how far do those frictional forces affect what's going on as you move away from the wall into the body of the particulate phase?
I think it quite affects all the particles inside the bed, as the wall affects the first row of the particles, but this row of particles, they are affected by the wall, affects the next row and subsequently the next rows. But you can expect that there will be a point that this effect is negligible, but it is not in the pseudo 2D bed because you have the other wall that is starting the same effect in the other side. So I think all the particles that are inside the pseudo 2D bed are affected by this wall friction.
So you could have a three-dimensional bed which was quite large, and those frictional forces at the wall would be felt.
In that case, I think this
quite a distance from the wall.
I really don't know. It will be depends on the ratio of particle diameter divided by the ratio of the particle diameter with the thickness of the bed. And we have preliminary postulated it on basis of dimensional analysis in the document, but we will have to check it with bigger beds and different beds and beds of different thickness to check in which ratio of this particle diameter thickness of the bed this effect is important or not.
Okay. Last question. The purpose of studying two-dimensional beds is to learn more about three-dimensional beds. What have you learned that's new about three-dimensional beds?
What I've learned about three-dimensional beds, that is not that easy to extrapolate the result from the 2D experimental beds to 3D systems. This is what I learned from 3D beds. That the things are not, the things you are looking at in the experimental or in the simulation 2D or pseudo 2D cannot be directly extrapolated to 3D. You have to be very careful with this data, and you have to know a lot about how to extrapolate this data to fully 3D systems. That's what I learned, that you have to take the things with caution.
Thank you very much.
You're very welcome.
Thank you.
Well, I have a couple of follow-up questions, and one is related to the simulations. You've done a lot of simulations in your study.
That's true.
And always the question is, what is the effect of the grid? So the grid size effect. And you have examined that carefully in the various chapters. But what I wonder now, is there a indicator which is of prime importance, which tells us whether or not you have a grid-independent solution. So what would be the best indicator for freely bubbling beds, in your view, to declare that you have a grid-independent solution?
You can check it with several variables. For
But there
example,
must be a best one.
the one that fits just the grid you want to show the data. I don't know. It's, for example, in the first chapter, I did it for several things. For several variables. I don't remember which ones. But typically, the authors take the value that is better for the results to show that the grid is independent of the results. But you will have to do that mesh sensitivity. If you want to do it properly, you should do that for all the variables you are showing in the result section. For example.
Meaning gas velocity,
For example.
solids velocity, pressure, and should we then focus on the time averaged data or the RMS data?
I guess both of them. I guess
Which one is more critical in your view?
It depends on the result you are showing. But for example, if you do obviously the time average result will be more often.
Yes.
That's the instantaneous values. So if you want to be more critical, you must show the instantaneous values. But for example, it's quite difficult to show the differences. For example, if you are taking the pressure signal and you are comparing the different pressure signals in the same point with different grids, what would you say that is the good one? I mean, you cannot show just the pressure signal because it would be different. But you don't know which one is the right one. So what you can do is, for example, to perform a Fourier analysis and to take the main frequency of the system and to check when this pressure signal gives the same frequency independent of the grid. For example, for the time average values, you can take the maxima in the time average because the instantaneous maxima will be completely different and will occur at different time instants. But for example, you can take the time average maxima or minimum velocities and check whether it is independent of the grid side. So it depends. I think it depends.
Well, our experience is that the, let's say, RMS data are more critical. Eh? So you sooner converge the time averaged solids, gas velocity and pressure and so forth, and that the fluctuating part is a more critical one. Eh? So that would be, in my view, our view, the best indicator. Another question I have is related to the improvement of the boundary condition for the wall. And you used in a very clever way the DEM model to construct a better boundary condition for the two-fluid model. And you also then involve the coefficient of restitution. But now I wonder which coefficient of restitution, because you have the particle-particle coefficient of restitution and you have the particle-wall coefficient of restitution. And they are not identical, as you know. So what should we use there?
In that study, what I modified is the coefficient of restitution between the particle and the wall.
Okay.
So I didn't remember exactly the data because I didn't set up the simulation. I only processed the data. But I think in the first part of this chapter, it is studied the differences between the particle coefficient of restitution and the particle wall coefficient of restitution. But in this part, I keep constant the particle coefficient of restitution, and what I modified in that table is the particle wall coefficient of restitution.
Okay.
Because it is the important parameter on the boundary condition.
Okay. And can you also explain to me how you would be able to determine that parameter experimentally? How would you proceed? So how can we drop? Okay, fine. Another striking, let's say, thing in the boundary condition is that you do not include the granular temperature. When you, for instance, look at various boundary conditions, so the Sinclair and Jackson boundary condition, then the fluctuating motion of the solids is included, reflected via the granular temperature. But you don't spend a word on granular temperature. Why?
I did so many work trying to include the granular temperature on the boundary condition, but in all the tries I did and in all the time I spent studying that, I didn't check any effect of the granular temperature or any realistic dependence of the boundary condition with the granular temperature. I tried it a lot because it's the main source that the main variable that you can relate with the boundary condition, but it didn't find any relation, any clear relationship between the boundary condition and the granular temperature.
So does that imply then that the formulations according to the continuum model do not make sense because you do not find any trend? So are they wrong then?
Maybe it's because I have to go deeper on the results, because, for example, the boundary condition depends on the solid velocity. So in the end, some way it will depend on the granular temperature. But at this point, I only check a clear dependence of this boundary condition with the solid velocity. And in all the tries I didn't find the relationship with the granular temperature. But it will be related because the velocity appears. So in the end, it will the granular temperature will appear also. But I didn't see any clear dependence.
Okay. Then I have a question on the DEM modeling. So there you also need to specify the fluid particle drag. And if I understood it correctly, you used for that information the Beetstra drag model. And in the continuum model, you use another drag model. Why not the same drag model? Because there should be, in principle, one best drag model.
Yeah, that's true. But when I did that in the first part of this chapter, when I did the first part, the Beetstra model, I think it was not implemented in the MFIX.
Okay.
So to make it faster, because it was also non-stay in Switzerland, I take the most similar drag.
That's a practical argument, not a principle one.
Yeah, that is.
Yeah. Okay. Okay, I see that. And then one final question on the DEM, and that's a bit a difficult one maybe, but nevertheless I will try to pose this question, since you have also formulated the model in your thesis, so I trust that you also have studied the physics of this model. And the question is related to the equation of motion for the particles. So equation 5.1 in your thesis, the equation of motion for the particles, so the translational equation of motion. And there we see the mass times acceleration is the sum of the forces experienced by the particle. And then we have minus the volume of the particle multiplying the pressure gradient. And then in the second term we have the drag. So beta is basically the drag coefficient in disguise, so to say. So it's a drag coefficient. But the drag coefficient, of course, includes the combined effect of the skin friction and the microscopic pressure distribution over the surface of the particles. So my question is, don't you account for the pressure effects twice? Because you have a separate pressure term, and of course in the beta, the microscopic pressure effects are included via the form drag.
That's true. Probably is because, well, you mean the value of beta according to the appendix. I defined this coefficient. So that's probably a mistake in the equations, because in the DEM probably this, as the equation is represented as it is in the document, but probably this parameter beta is implemented different in the DEM.
For the beta, you have the drag closure explained in your appendix, and they are correct. So that's not my concern. My concern is
that if I account it twice for the value.
Yeah, because you have the gradient of the pressure acting on the particle. So gradient of the pressure is the force per unit of volume multiplied by the volume. So that gives you a pressure force. But also in beta, you have a contribution of the pressure force. When you would examine the beta in a limiting case of one particle, it's basically the Schiller and Naumann drag correlation, and then you have at low Reynolds the skin friction, and at higher Reynolds you have the form drag, or in other words the pressure distribution, which dictates the force. So once more, you have basically two pressure terms in your equation of motion. Is this correct? Yes or no?
As you have said, it should be not. But I think this the value of beta is not the implementation in the DEM of the momentum interchange would be different than than the equations I put in the appendix.
So you think this equation is not correct then in the
No,
end?
I mean, the equation is right.
The equation is right, but?
Parameter beta that I put in the
Yeah.
appendix is not just the same as it is implemented in the DM. So all the
Now I'm confused at a higher level, so to say.
all the momentum interchange coefficients I put in the appendix refers
Yeah?
as they are implemented in the two-fluid model.
Okay.
Not in the DM. This is the main equation of the DM. So maybe this confusion is because this parameter beta, this momentum interchange coefficient, is referred to the implementation in the two-fluid model, but in the DM it should be different.
But couldn't it be that the pressure in this equation has a different meaning than the microscopic pressure? You know, you have the detailed pressure distribution over the surface of a sphere, that's the microscopic pressure distribution. And this pressure in equation 5.1, maybe that has a different meaning. Have you thought about that?
Not really. I didn't go so much inside the DM.
No. Okay, that's the explanation basically. This is the macroscopic pressure gradient, which is different from the microscopic one, which dictates the form drag. Eh? Okay.
I'm more familiar with the two-fluid model than with the DM, so sorry.
Yeah, I know.
Not
But,
answering right.
well, as said in the introduction, you have included in your thesis the description of the model. So I, for that reason, also asked the questions about the model. Well, then we come to the two-fluid model. One more detailed equation on the radial distribution function. So it's in your appendix, equation, I think, A33, page 167. So what will happen with the radial distribution function when the solid's volume fraction approaches the maximum packing fraction? What should happen to the radial distribution function? Do you know?
You cannot implement, you have the simulation crashes. You cannot implement this equation directly. You have to add a small term here to make that the denominator is not equal to 0.
But it will not happen in this case. As the equation, as you write it down, that's always non-zero, the denominator.
Yeah, but when you can...
So my question
So
is
the point
basically...
is, if you have a solid volume fraction of 0,
Yeah.
sorry, I was wrong. You have 1 divided by 1? No, it is 1.
solid volume fraction can equal epsilon solid's maximum. So then the maximum value of that ratio is 1. Raised to some power plus 1 is non-zero.
Yep. It was,
So something is wrong with this equation.
yeah, maybe I wrote it wrong.
Yes.
Oh, sorry for
So
that.
what's wrong? You already gave the answer implicitly, basically. Eh?
So that the equation is wrong because it goes to 0.
Yeah, so the plus should be a minus. So in that case, you can have a situation that it goes to infinity. A small technical detail, but I'm confident that you have implemented it correctly. Otherwise, you could not have obtained the beautiful results as reported in your thesis. Thank you.
Sorry for that mistake.
I've just got a few questions. A general question about the predictions of the simulation. For example, on page 70, figure 3.5.
Oh, sorry.
All the pictures of bubbles, and I've seen this in other people's simulations, show a gradation of voidage fraction, so that you get the volume fraction of solids varies gradually as you approach the bubble, so that round the bubble there's a low voidage fraction with perhaps only 20% of solids. And I don't think that's what you see in experiment. This is not a comment, just a comment on yours. I've seen it in other people's results.
So that's true. That's If you mean the visualization of bubbles in a
No, when you look at a bubble in a two-dimensional fluidized bed, there's quite a sharp boundary, and it's pretty clear that the volume fraction of solids just above the boundary is pretty close to what it is everywhere else in the bed, whereas these simulations show a gradual gradation of volume solid fraction. And I think that's not just yours. I think I've seen it in other people's. And I wonder if it's giving the right answer, that's all.
Okay, so it is related to the modeling nature of the two-fluid modeling, which deal with treat the two phases as fluids. So in the end, it is a continuum media. So you have not exactly this the high gradient when in the bubble control.
So you think this is a necessary feature of the simulation? Because I don't think it agrees with the experiment. Now, this is not just a comment on your simulations. I think everybody else will do the same.
So I didn't get it very well. I go here again. So can you repeat?
It's the gradation of color as you approach the bubble.
Yeah.
Which suggests that the volume fraction of solid is varying gradually as you approach the boundary of the bubble. And I don't think that appears on the experiment.
But it's quite difficult to measure in the experiment this gradient of when you are approaching the bubble, this gradient of the solid concentration when you are approaching the bubble.
Well, I think people have measured void fractions and they change pretty sharply. I think
so
there's something funny about the simulation, not just yours, but I think everybody else's does that.
Yeah, well, I think this is related to because of the two-fluid modeling, because it's you have to have you cannot have sharp gradients between the both phases, not as sharp as in the experiments. Yeah. So you have to go in some kind of
you have to have a gradation shape. Yeah. Thank you. Then on page 42, equation 2.7.
I have now the equation 2.7.
It's the formulation of equation 2.7. There's a term called U sub TH, which is the through flow through the bubble.
Yeah.
Now that's related to the per unit of distributor area. And I wondered if it wouldn't have been better to, the equation is perfectly correct as it stands, but to be consistent with the through flow velocity in later chapters, you should have multiplied UTH by delta sub B, so that the through flow is related to the bubble volume. And then you would, because on page 44, you get very low values of U sub TH because it's related to the distributor area, whereas I think one would like it to be related to the bubble area. This is just suggesting a different method of analysis. I think that would be consistent with what you've got in chapter 4 about cross flow between the bubble and the particulate phase.
Okay,
and then Professor Hayhurst commented on the distributor. I would have liked to have seen a pressure drop calculation. I myself did a calculation, which I'll give you, as to one usually tries to get the pressure drop through the distributor comparable with the pressure drop through the bed. And I think you have got that, but it might have been useful to give it in the thesis.
Okay, I did the calculation. I characterized the pressure drop along the distributor,
and it was adequate. Yeah.
So
the other question about the distributor, would your simulation run to simulating discrete gas input?
Well, that's a very interesting question. I didn't simulate its individual.
I'm not suggesting you should have done it, but just asking, could it be done?
It could be, but it's quite difficult because you have to have such a level of resolution in the mesh that is quite difficult to approach.
Yeah. You need a very fine mesh near the...
You should need a very fine mesh near the orifices. So, for example, if the whole mesh has this mesh size, it will be almost impossible to simulate in as I carried out the simulations in a desktop computer, and also it would quite difficult to change the size of the mesh when going up.
When you're going up, yeah.
So, but based on the activation region mechanism that tells that the 5 centimeters above from the distributor, all the bubbles are homogeneous, and it does not depend on the jet effect of the orifices.
Quite so, yeah.
So, in the end, in the simulation, what you don't have to do is to go very close to the distributor, but the results 4 or 5 centimeters above from the distributor will be properly compared.
The final question is about the basis of chapter 6, where you, I think on page 138, no, I'm sorry, it's page 136. You assume that the frictional force between the particle and the wall is proportional to the velocity. And my understanding of friction is that there's a static friction coefficient, and then once you get movement between the surfaces, the friction is reduced and maybe independent of velocity.
Yeah, that's true, but in the test I did for this functional form, which tell us the dependence of the frictional forces, I consider just a constant. I use also the value of the velocity and the acceleration.
Yeah.
And what I see is that the lowest values in the discrepancy factor that I defined in the document was obtained for when the functional form omega is equal to the velocity, and also a very illustrative finding was, I think it is not included in the document, but it is included in the publication of corresponding to this chapter. That is the visualization of the pressure signals. For example, this is the in figure 6.7. This is the simulation. Sorry.
On the same chapter, you show various diagrams, page 152 and 3.
Yeah, in the figure on page 153. There you can see how the pressure evolution, the time evolution of different pressure signals, and the pressure calculated using including the frictional forces is the black line. These frictional forces are calculated using the functional form omega equals to the velocity, but I check if you use another functional form, such as considering this as a constant or the acceleration. What I found is a completely unrealistic behavior. So instead of a continuous behavior that we can find here, that can reproduce really good the pressure direct measure, what I found is that when using a different functional form, the signal was discontinuous.
And you think these fluctuations are due to frictional force? Because I would have thought they might be due to bubbles, but...
Yeah, the fluctuations are induced by the bubbles. What I think is induced by the frictional forces is the displacement between both signals. I mean, the displacement between the red line and the blue line. The red line that corresponds to the pressure calculated without considering the frictional forces, and the blue line that is the pressure direct measure. Yeah. It is not the oscillations are completely related to the bubbles, but the shift in the amplitude and the shift in the little shift in the frequency that appears also is related to this frictional force. I think it's related to this frictional force.
Because I was a bit puzzled by equation 6.12, which writes down a mass acceleration equation for the whole bed as if it was moving with one unit, with y sub cm as a coordinate of the mass. And you know, a bubbling bed isn't just one but a bit of particles, they're all moving at different velocities. I wondered how you justified using a single coordinate to specify the position of the whole bed.
Yeah, I should have used both, but I think the position in the lateral coordinate is not that important as the position in the vertical coordinate.
Yeah.
I think I didn't. Yes, you have. I should have included it, but as to simplify the calculation, I think it would be differ that much if I should have included the lateral coordinate, and I think the quite important is the vertical one.
Yeah. Good. I think that's all my questions. Thank you very much.
Very well.
And thank you for the presentation, which was very clear.
I think we can ask the audience if they're to leave.
Are we to ask the audience whether they want to ask any questions?
Oh, that's right. That's
yes,
right.
Yes. Does anyone have any questions from the audience? I think we've given the candidate a pretty good run for his money, so if there are no questions, I think, do we declare the session closed at this point? Yeah. Well, thank you very much, and thank you to the candidate for answering our questions and for the splendid presentation. Good. Thank you.